Welcome back. In this lesson, we're going to prepare to derive the equation for planes in R3 by first looking at lines in R2. Let's recall that when we were talking about lines, you were probably most familiar with the explicit function equation for lines. This equation starts by looking at a given point. Let's call that point P naught, or P sub 0, which has two coordinates x naught and y naught. In addition to a given point on a line, we start with a slope, which we call m, usually written as a ratio b divided by a, where we rise b units and we run a units. If we have a point and a slope, many students in pre-calculus and even calculus look at the explicit function representation of the output variable y of any point on the line as an explicit function of input variable x. And generally we write this as the slope m outside of x minus x0 plus y0. And this explicit function has a very famous name. This is called the point slope form of a line. It's explicit because the output y corresponds to input x, and y is isolated on the left-hand side. Notice that in this form of a line, we have explicitly encoded output in terms of input. This explicit representation depends on the slope. In other words, there is an explicit reference to the slope b over a. And we can take a look how to use this general form, which we're quite good at this point in our career. So suppose, like we did in lesson 5, you're asked to find the explicit function representation of a line through point 0, -2 with slope -1/2. Here we graph this using the plot command in Mathematica. We see that our output variable y would be given by m outside of x minus x0 plus y naught. I'm getting a little ahead of myself here. This would be y 1/2 with a negative minus 0 minus 2, since y naught would be minus 2. And of course this is -1/2 x minus 2. This is my explicit function representation of that line. And we can see that this holds true. Here we have the point P naught. And then we look as we go down 1 and over 2. And here's my next point on the line, which is at -2, -3. We go down 1 and over 2. We have 4, -4, etc., etc. We saw that from this explicit representation, we could also encode a vector valued function. So when we think about this vector valued function, r of t, which was x of t, y of t, and we saw that the vector valued function was given as a point on the line plus t times a direction. For the slope m equal b over a, that means for every a units we go in x, we go b in y. We saw that this corresponds to the direction vector a units in x, b units in y, which means in our case, when we have m is equal to -1/2, v would be 2, -1. You see it? So 2, -1. And then the point on the line would be the same point that we started with, which was 0, -2 plus t outside of 2, -1. and this now becomes the parametric equation 2t, and then we have something like negative 2 minus t, and this gives us a way to represent the line in one-dimensional input, two-dimensional output. The reason that this is kind of useful is because this direction here, again, explicitly referenced the slope. So this is an explicit slope to slope m equal negative 1/2. As we spoke about in the last video, it's also possible to encode curves implicitly. So in order to do so, I want to notice that the slope m equal negative 1/2, which was the direction vector 2, negative 1, corresponds to a unique orthogonal direction. Meaning to say that when we have, here's the exact same line, here's our point P naught, so let's call this thing right here P naught. This direction here, so the direction of this vector that connects any 2 points on the line, and maybe we call this point right here P, that direction corresponds with a unique orthogonal vector, which we're going to call n. And by orthogonal, we literally mean perpendicular, that these are at a 90-degree angle. And I hope the dot product is in the background. And notice that if m is negative 1/2, but in general we could write this as b over a, then when you write v, we saw that v was a comma b, and then immediately remember that the orthogonal vector is going to have a 0 dot product. So in order to have a 0 dot product, remember that the slope orthogonal to a over b, so if we wanted to talk about m perp, would have to be the negative reciprocal. So this would be negative a over b. And then this would correspond with our normal vector, which would say go b units in x and negative a in y. And in this specific case, for the particular vector that we're looking at, recall that this was 2, negative 1, which would mean that this is negative 1, negative 2. So that means go down 1 unit and left 1 unit, or go right and up 2. So there's that n there. And we can check real quick that if I took v dot n, the direction of the line dotted with the direction of the normal vector, that indeed we would get 0. So here we would have b negative a, and here we have ab minus ab, and we get 0, which confirms that this normal vector is orthogonal to that line. The reason that I wanted to talk about this is this gives us a way to reconceptualize lines. So instead of thinking about the line as the set of all points that satisfy this equation, let's encode the line using an implicit relation equation based on orthogonality. In other words, we'll define the line as the set of all points, in general p of xy, such that the vector connecting the point on the line p to any point p naught to any point p is orthogonal to the normal vector n. So if we look at this description, this would mean that n dot x would have to be 0, where x went from the specific point that we know is on the line to any point on the line. But that would mean that x was given by the general point x minus x naught, y minus y naught equal to 0. And then we knew that if the vector v encoded the slope as the rise over the run, so the slope in this case would be b divided by a, then the normal vector had to be the negative reciprocal, which would be to switch these components and slap a negative on one of them. So when I go ahead and substitute that in and do the calculation out, I would get something like b outside of x minus a, x minus x naught plus negative a outside of y minus y naught equals 0. And then of course we could distribute, so this would be bx minus bx naught plus negative ay plus ay naught equals 0. And then we could do a little bit of magic here and then just bring the constants onto the other side. So this would be bx naught minus ay naught. And of course, if you wanted to, you could write this as ax plus by equals c, right? Or if you wanted to call this negative c, this would now give us ax plus by plus c equals 0. And now this is the exact implicit representation in general form. Here we have a expression in terms of x and y. The right-hand side is 0. None of them is solved for the other. And if we looked at this in the specific case that we had in the example that we had considered, so remember that the slope in this case was negative 1/2, which implies that the direction vector of the line was 2 units along x for every negative 1 along y, which implies that our normal direction is the negative reciprocal. And in this case, I'm going to do the opposite negative reciprocal. I'm going to switch, turn this into a positive, and then just switch the x and y directions. And then we just said that when we wanted to look at every point on our line would be given by some general p. And then if we looked at any vector from our original point to this p, this would be x minus 0, y plus 2, since p naught is 0, negative 2. And then here we would have 1, 2 dotted with x, y plus 2 equal to 0. And this is where we have our explicit representation. This is now x plus 2 outside of y plus 2 equals 0. And then this is now x plus 2y plus 4 equal to 0. Notice y is not explicitly written in terms of x. And this is now our general implicit form. And this implicit form was based on the dot product. Two vectors are orthogonal if and only if their dot products are 0. Some folks have called this standard form of a line. And the standard form from a line depends on the dot product, which you might not have seen before. The reason that this is super important is the same intuition that we use in this implicit relation, which is to say that a line, when we think about a line, this is kind of the picture that I would have in mind. So this is the general line. We have some exact point on the line, and then we have a general point on the line. So this is what we call x, y. This specific point is x, y, 0. So I'll call this specific point on the line. So that's p naught. This is going to be some general point, the one that we want to collect. Every general point are the ones that satisfy the equation of the line. One way to look at the line is to try to get the output in terms of the input, but another way to look at the line is to say, if I look at the vector x, which goes from a specific point on the line to any point on the line, the way to collect these is to say these points, when we form this vector, should be directly orthogonal to the unique normal direction. I hope I didn't say earlier that the normal vector was unique. The normal vector is not unique, but the normal direction is unique. So in other words, we define a line in this implicit equation as the set of all points that form vectors orthogonal to the unique normal direction, encoding the line via its normal direction. So notice the normal direction implicitly gives rise to the direction of the line, and it's an encoding information. Could you guess how we define the equation for a plane? In the next video, we'll get into defining equations for a plane. See you there.